Stop. Yeah. So I got a mail from your representative saying that you guys want an extension of the submission of the assignments. So which is perfectly fine with me, but as I told in the mail there also, that supposedly you guys are struggling with some of these stuffs that has been done so far. So can you just tell me actually what all doubts you have? I mean, since it is the beginning of the class, I really don't want to lose you guys. So which points are you finding it difficult and so on?
Sir, suppose we are given a problem. So suppose we are given a problem and we are asked to devise an algorithm for solving that problem. So in that case, so obviously we should write a pseudocode for that. And do we need to prove that that this algorithm works?
Yeah, I mean, so if you write a pseudocode, then you of course need to prove that it works. But if the pseudocode is kind of very simple, okay, I mean, so this is a place, right? So pseudocode is very simple. You can write just a couple of lines. That okay, see, it is obvious to see that this is what is happening in these 2 lines. So since it is in the beginning, so none of the codes that you will write will be too complicated. Of course, later on it will become more and more complicated, and then you have to write it. So if you have a for loop, maybe you might want to write a what is called loop invariant and so on. So you have to give a formal proof of correctness of the algorithm. Yeah.
Sir.
Yeah.
And also, like some problems require, let's say, like some problems specifically mention that like you can think in terms of, let's say, heap sort, or maybe some problems might require a rearrangement or some sort of form of sorting. So in that particular situation, can we, like, since it is done in the class, so do we have to include the code for sorting also, or we can assume there is a routine called like merge sort?
No, you can assume that. If
we can assume that.
Yeah,
so
yeah,
we state that assumption, and then we can use that as a routine inside our algorithm. Right?
So you have a list of points and you want to sort it.
Yes, sir.
Okay. I mean, I'm assuming that I'm not asked you to sort it, right?
No, obviously something else.
Yeah.
Yes,
so then you can have this okay, use merge sort to sort it. Okay, that's perfectly fine. And you can assume that okay, so that will take ordered n log n steps. And it's going to give you the correct sorted. I mean, after you do that, you have a sorted array. Okay. Yeah.
Sir, so can we ask something from the assignments? I mean, from the assignment?
you can ask. I mean, if it is just asking me to solve the assignment, then
no, sir, not like that. I mean, I was asking for a general intuition.
Yeah.
That, sir, suppose we have some algorithm. I mean, so we have some problem, and so the problem. I mean, suppose we are dealing with an algorithm which is probably not recursive. Now, if the algorithm is recursive, we can simply write a recurrence for that and try to solve that using our own intuition or master theorem, any one of them. Now, if the problem is not, I mean, if the algorithm is not recursive, and suppose we are required to show that the algorithm has like big O of log n or log n square or something like that complexity, then can you give us a general kind of intuition that how can we approach that kind of problem?
See, it's like, so if it is not recursive, right, then what does an algorithm have? Right. So the algorithm will have some kind of a what we call as this. Say what is basically, say you have some initial parts, right? Some few lines here and there, which are like the initial setup. Maybe you have some other calls, say you have done some merge sort kind of stuff like that. Okay, so you have this, the input is, you have the input, maybe input is S and you do some merge sort. So these are like all in a standard one line. It's a linear program, what we call. Not linear program, but it's a straight line program. Okay, that you basically do one after another steps. So then the time complexity just adds up. Okay, so this one takes order n, this one takes order n, or this one takes order n log n, and so on. And then what you have is you can have a for loop or a while loop or whatever, right? So for something, and you do some kind of stuff. Now there, what you have to do is that you have to ask, so you're doing some for loop, right? How many times does the for loop happens? Okay, the loop happens n times, okay, fine. And within each loop, I do some stuff, which also takes, makes order log n number of steps. So the time complexity for the whole for loop is n times of n log n times log n. And you continue after that. So this is how any program is, right? Any pseudocode is, if it is not recursive. Okay. If it is not recursive, then it is just a set of steps done in a linear fashion or in a straight line fashion. Then you have some loops. Maybe they will have multiple loops, one loop inside another loop, but then you have to calculate it accordingly, like how many times the loop happens. So every loop is a step, right? And within each loop, how many things are happening, and so on, and finally you can calculate it. Is this clearer?
Okay, sir. Okay, sir. Thank you.
Yeah. Any questions? Any other questions? I can see a chat coming. This is not related to any question, but is it mandatory to type our solutions? No, not. See, again, in general, I insist, particularly when I teach in the master's level courses, that everybody has to type their solutions in LaTeX and submit it. The reason is that so that they can also get used to this writing of LaTeX. Now, for undergrads, I will not enforce that particular case, but learning of LaTeX is a very useful tool to have. Okay, so if you do it, it will be good for you in some sense. I don't know how many. Do you guys have anyone of you use LaTeX, or how many of you know LaTeX actually?
Do know, I think most of us do know LaTeX, but it's very time consuming.
It is not time consuming. Okay, so you know LaTeX, you know the syntax. Like for me, for example, I would be more comfortable writing in LaTeX than in a pen and paper. I mean, of course, what happens in LaTeX is that I might write something and I find that, okay, this is not a very good explanation. So I can edit it easily, right? In a pen and paper, that is not something that I can do. So, so it's all about, I think if you learn, I mean, it's not time consuming at all. Math equations and all, they can be written up. So it requires a little bit of practice, and that's it. Yeah, so somebody says that, can you give some help how to approach question number 5? Now, can you please tell me what is question number 5?
Sir, I guess that fake coin one. You have in many coins and that one?
No, fake coin is number 4.
Oh, okay.
I think this is the is it the comparison, the average comparison?
Sorry. Oh, the lower bound thing, is it?
Let me just wait, sir. I will also.
Yeah, I mean, I'm trying to open it up also.
Sir, someone has written it down in the chat box.
Oh, given an array on n such that the elements are come up with the order n. Okay, so once you have an order n algorithm, okay, so it's the hint is there in the question. Okay, the hint is there in the question. So you have been given n elements, right, in a big in a finite range. It's not arbitrary range. Range is from 0 to n cube, now -1, right? And your job is to find a sorting algorithm for the elements. Now, what all things do you know about the sorting algorithm?
Sir, we've learned counting sort in that tutorial session last week.
So first of all, look, you have learned a lot of other sorting, right? You have learned merge sort, quick sort, and so on. But none of them does in order n,
Right.
right? So that is not what can be done clearly, right?
Right.
So what you have to do is something of where this counting sort, or maybe even this bucket sort or attic sort kind of stuff like that, that possibly was also explained a little bit in the class. So that has to be done.
Sir, here we don't have a discrete set, right? This is all real numbers from.
No.
0 to 10.
No. Okay, so there was a big misunderstanding. So whenever we write it in this bracket, this bracket is there. Yeah, so no, so this is a discrete set. So maybe it was not written up very well.
Okay, good.
Okay, so this is a discrete sets. So sets between 0, 1, 2 till n cube minus 1.
So the elements are all integers.
Are integers.
Sir, even if they're rationals, so should we have a problem there?
Yeah, you'll have a problem. You will not be able to do it in order n.
Okay.
Sir, but now that we know that these are integers, the bound itself really doesn't matter as long as it's finite, right? It could be n to the power 100.
Basically.
Right. Okay.
I mean, that 100 will come in the picture, but 100 is a constant, so that will go into that ordered notation of n.
Right.
Okay. So that's the hint that's there for this problem.
Sir, I had a doubt regarding number 3.
Number 3. Okay.
Which was to find a Pythagorean triplet in order n squared.
Right.
Using the indices. We have to find the indices of the Pythagorean triplet, if it exists.
Yes.
Sir, in this, can I propose a solution and then ask something about it, or would that be?
Maybe, so, I mean, tell me what you want to ask, maybe, even without proposing the solution.
Okay, sir, I don't know how to not reveal much, but essentially, can we use a counting sort kind of?
Yeah, you can. There's no
Argument
problem with that. Yeah. You can use sorting stuff.
So, but counting sort will require some space, additional space. So that should.
So I'm not really worried about the space. Okay.
Okay.
See, I mean, as long as the space is order n, that's perfectly for order n square. Number of steps is ordered. When I say number of steps, okay, so this is something that you should say, that if I say the number of steps, then you already have the number of space is also bounded by that.
Okay, right.
Okay. In some sense, because otherwise, how would you be able to use it or something like that?
So, but then there is no bound given to us on the actual the set of numbers that we could have.
No.
So, if we were to just determine the maximum element in order n, and then use it as a bound, would that?
That's fine. It is good enough.
Okay.
But see, then the issue is that if I have given you maximum number, the maximum number is not a constant, right?
Right.
Maximum number can very well be n to the power 100.
Okay. Right.
Okay. So if you want to now create a space of size n to the power 100, then that's already n to the power 100 steps.
So that definitely won't be able to give us an n squared.
Yeah. That will clearly not give n squared.
Okay. Right.
Sir.
Yeah.
Sir, in the number 3 problem, that peak of n square. So, is it possible to design an algorithm which keeps the running time is bounded by big of n, or means less than big of n square?
Yeah, of course. I mean, is it possible you are asking, or? I mean,
yes, sir. Is it possible? Hello. Hello? Oh.
Most probably not, but I mean, I don't have a lower bound exactly right now.
Sir, can that be proved?
No, I don't have a lower bound. I cannot prove it right away.
Oh, okay. Sir.
Chandramoli, could you repeat your doubt?
So my doubt was that in question number 3, it was that find the Pythagorean triplet in big of n square. Is it possible to find the triplet in less than that bound, the big of n square?
Okay.
Yeah, I'm not 100% sure. See, even if you guys cannot find a thing of big O of n square, okay, so I would still say that in the assignment you can write the best algorithm that you can find. Okay. So if you cannot get big O of n square, but you can write it in big O of n square log n, just write it down. Write that algorithm. Okay, so I mean, it's important that we know, I mean, what is the best? I mean, we should have an efficiency in mind and try to write the best algorithm that we can come up with. Okay, you'll get partial marks for that for certainly, and also he will help you in the thinking part. To start with, what is the worst algorithm can you think of, or what is the most trivial algorithm that you can think of? Yeah.
Sir, regarding problem 3, sir, if we we use comparison, okay, but if we use other things like squaring or something like that, do they also?
You can assume that the squaring and all is order 1.
Okay.
Yeah,
No, but if that is order 1, but like squaring all of them together is order 1.
No.
Or
Squaring
like,
a particular number is order 1. So all of them squaring is order n.
Okay, sir.
Okay. Oh, so Ananya Brother had written that whether I mean, is it fine to not write the questions on the laptop? It is perfectly fine, as I told you. Okay, I'm not asking you to write it on the laptop. I'm not insisting you write it in a I mean, write it in a properly, neatly in a question in a paper. Try to write, and this is something that what I'm saying now is true for any exams that you will be doing in this course, and possibly a good advice to have for any other courses also. Just try to write the questions, every question in a different paper. I don't think there is a shortage of paper that you have to save paper on that. Write every question in a different paper, or basically on a new paper, and order the problems. I mean, order the problems. Basically, the first page should have the starting of the problem 1. Then after some time you have problem 2, and so on. So that when we correct it, particularly in the online setting, when you correct it, it becomes much easier. And else, I mean, finding out whether you have written problem number 3 somewhere in the paper, it becomes very hard. Okay, and of course, write it in the most neatly and number the problems very clearly. So these are the things that you should do, and otherwise, that's perfectly fine.
So can you give some hint about how to solve the fake coins problem?
The fake coins problem. So the fake coins problem is actually hard. Okay, I must say. So the first thing that you can think of is, can you find out whether the fake coin, number of fake coins, is odd or even? Okay. So say if you can find out, how does it help? So look at the number of fake coins. Okay, if number of fake coins is odd, I know that the last bit so let's say k is the number of fake coins. So if I write k in a binary form, right? So what is the length of k? It is log n, right?
So sorry, sir, could you please repeat?
Yeah, sorry. So I have these fake coins, right? I have n coins, all total, right? Say
2 in coins.
Sorry?
Sir, you have 2 in coins. You
That's fine. Okay,
mentioned in the question.
Yeah, this, okay, the 2n, okay, it doesn't really help that much in that respect. Okay, so don't worry about this 2n. Actually, it doesn't matter. I think 2 is a bit confusing maybe for many of you. Yeah, so forget this 2. I mean, you can think of n coins only. So it's not, 2 is not giving too many extra information actually. So don't get sidetracked because of this 2. Okay, so say k is the number of fake coins, right?
Sir, I joined a bit late. Are you solving the problem?
No, I'm not. I'm giving you hints here.
Okay, sir.
Okay, so I have this 2n coins and I say that k is the number of fake coins. Then how will you write k? How will you give the k? How an algorithm will give k? Okay, so best way of thinking is that if we write k in binary, okay, so basically it is a set of numbers. So basically I can say k1 to k log n, right? So it's a log n bit binary string, right? So that means you have to give me that log n bit binary string, which is the k, because k has to be less than n, so this total length is binary. Now, to start with, let's say what is the last one? Okay, what is, that can be the first question. What is k log n? Meaning, what does this mean? So k log n is 0. What does it mean? It means that the number k is even.
Even.
Right? So k log n is 1, meaning that k is odd. So this is a start. Try to find out the hint. Okay, the hint is that first try to find out k log n, the last bit, or basically forget k log n. Try to find out if k is even or odd. Okay. That will be the first trick. And now see, as if you can understand it very carefully, see there are log n different possible bits, right? So one approach would be to find each of these bit in order log n. So question is that can you find this one in order log n? So if you can, okay, so maybe I will give you some more hint. Okay, so say S is the set of, S be the set of points. Now if I can partition S into two halves, S1 and S2, disjoint partition, such that the number of fake coins in S1 is equal to the number of fake coins in S2, then what do I know? Then I initially, so if I can do that, okay, then I wanted to initially find the number of fake coins. So number of fake coins, so the number of fake coins was this one, right? K1 to K log n. Then I already know that K log n is 0 and what? And I can now throw away S2. And I can just say that, okay, now count the number of fake coins, count the number of fake coins in S1. So say this count is something, right? So what will be this count? Can you tell someone say what will be this count be?
K log n minus 1.
No.
So it will be k by 2, right?
K by 2, right? This is
Oh,
exactly
right.
K by 2, which is in the language of this binary string is what?
First digits.
First log n minus 1 digits, right? K log n minus 1 digits. And you already know that the last one. Okay.
So here we have to ensure that S2 has the odd one coin, right?
S2, so you have seen odd one coin?
So
Yeah,
whether
so
it
you have this same number of coins. That's all you have to do.
so, but K might be odd, right?
What happens if K is odd? Okay, so that problem.
Oh, okay. Here we were assuming that they were equal. Okay,
Yes.
sorry.
Even if it is even, then we do this thing.
Okay, right.
Now, if it is odd, then I would like to do something slightly more complicated, but not too much. Again, I have this S. I want to partition it into 3 parts: S1, S2, and maybe 1 or 2 coins. Okay, so maybe another set S3, such that what number of fake coins in S3 is just 1. Number of fake coins in S1 is equal to number of fake coins in S2. And if you can do that, then you can go back to the same thing. Then again, what happens is that you can have this K log n, the log nth bit is actually 1, and you can just do the same thing again. Right? Because the number of fake coins in S1 is nothing but K minus 1 by 2, which is K1 to K log n by 1, log n minus 1. Okay. So the all goal is basically how do you split S into this set or this set. Okay, and that is all that you want to do. So think about that.
Sir, do we have to write it in code?
And first solve it and then write it.
Yeah, I mean, if when we have solved it, do we have to write it in pseudocode or even in actual code?
No, you don't have to write it in actual code for certain. Okay, writing it in a pseudocode is a good habit to have. But also explaining this kind of, if the algorithm is too complicated, writing it in simple steps is also fine. Okay. Actually, for like this problem, actually it is quite complicated to write a pseudocode also. So you can explain it in your words. But try to try to explain in words step by step. Each step try to explain in words.
Sir?
Yeah.
Sir, could you explain how heap sort relates to the numbers, the 6th problem?
The 7th problem, right?
7th.
I'm sorry, the 7th problem.
Yeah, think about it. This is something that I will not do.
Sir,
Yeah.
for the
It's not heap sort, think of it heap.
sir, for the 5th problem, where we have to find a sequence which has closed bound 0 to n cube minus 1, and we have to sort it in n steps. They are all integers, right? They're not real numbers.
They're all integers. Yes.
Sir, I just wanted to ask that the 4th question was a bit complicated to think about, to come up with.
Yes.
So is this the sort of algorithms you're expected to be able to crack?
No,
in
this is
an
a
exam
bit, I mean, among this set of questions that are here, the 4th question is hard.
Okay.
Okay. So 4th question is hard, and yeah. So you can also take it as a kind of a star problem kind of stuff like that.
Okay.
But it will be fun. If you solve it, you will realize the beauty of certain very
Right.
basic concepts that you have learned.
So it won't be an exam question, but it's just an
Yeah.
illustrative problem.
Yeah.
Right. Got it.
Yeah, it's a mixture of this paper has a mixture of questions, right? So many of them are so easy, some of them are hard. and so on. Yeah. Any other questions? Yeah. So no other questions for now. Okay, so that's good. So in that case, let us try to move ahead. Okay, so you guys try to solve it. Okay. By the way, it's a. I mean, I would insist that you guys not only try to solve these assignment questions, but also the problem set questions. The reason we are taking the pain to upload problem sets is exactly because, I mean, these are the questions that, I mean, if I could have just evenly told that, okay, go ahead and solve all the questions of this chapter from these books, and I don't think you would have done. So we have basically picked up various questions from various places, maybe made some of the questions, and they are there. So please do them. Please try to solve them. I know that since it is almost a first course for you guys to think algorithmically, so that requires some different kind of way of thinking. Okay, so it will take you some time, but please try to do that, and feel free to ask us as many times as you want in the class, in the tutorial. If you want some extra classes also, or extra tutorials also, we can try to arrange for that, sort to clarify your doubts on this kind of stuff. Okay. Hello.
Hello, sir.
Yes, sir. Yes, sir.
So should I go ahead with the next topic now?
Sir,
Yes, sir.
just another doubt.
Yeah, sure.
Sir, in the last tutorial class, we had discussed bucket sort,
Yes.
but I couldn't really understand that fully. So should we take it up again in the tutorial class? Or?
You can take it up in the tutorial class, but the bucket sort thing, I don't want to really hang around with this kind of this bucket sort kind of stuff too much.
Okay.
The reason is that see, there are lots and lots of sorting algorithms. Okay, the reason we wanted to give you just a sample of sorting algorithms says that, okay, the comparison sorts, there is n log n algorithms, there is a lower bound, there are various algorithms have various properties that we want to preserve, and if you are given some prior knowledge, like the data is all are integers and so on and so forth, then you can do something better, and that is what the counting sort or bucket sort or the radix sort, all of this kind of string stuff. Okay. Now, if you have not understood it, of course, you can ask us or ask the tutorial once again. But the other thing also that you can do is that try to read it up by yourself from the internet or in the book. If you don't understand it, then do come back to us.
Okay, sir. All right.
I believe that you will be able to follow it once you read it from the book or the internet.
Okay.
Sir, does bucket and radix mean the same thing?
No, I think they are different. I mean, I also forget actually which is called what, honestly speaking. There are some very subtle differences here and there between this stuffs. I think they are slightly different. Yeah. Yeah, I mean, it's like, I think both of them are sorting strings, if I'm not wrong, sorting some few digits, k-digit numbers, integers, and they sort it digit by digit. Basically, that's the basic idea.
Sir, that's why I was asking that in the problem number. Which one I forgot?
Yeah, 4.
Yeah. So that problem where in q minus 1.
It's not the counting sort. Counting sort is different. Counting sort, in that case, you don't do anything. It's like you make a huge thing and store it there, right? Then you have been guaranteed. So, like, I mean, there are two. The counting sort is the place where you kind of you are guaranteed that the input or the data are from 1 to k. So then make an array of size k and just keep frequencies of those.
Right.
Okay, but that will take order k space, and that means order k time also, right? So that is counting sort. But if bucket and radix sort uses the case when you have been told that all of them are k digit inputs. Okay, and if they're k
And we saw digit by digit, right? Compare digit by digit.
Digit by digit kind of stuff.
Right.
Okay, so now question is that here what happens? What are the digits kind of stuff? How many different is this? Can you write this n cube things? I mean, all the numbers between 0 and n cube as 3-digit numbers, 4-digit numbers, something like that. Think of it. Okay, I think I'm giving you way too much. Okay, I mean, what does digit mean? Does it always have to be decimal, or can it be? It's a label kind of stuff. Can it be just n labeled things or something like that? Okay.
Okay.
I think your Omkar is here. Omkar, are you there? Do you have any suggestions about this question, about this assignment questions?
So which question specifically?
I think they were asking about quite a few of them. Yeah, I think these fake coin ones, the sorting on when the range is 0 to n cube.
Yeah, so in question, so for question number 4, sir has given quite enough hint. For question 5, so again, sir has actually given quite a lot of hint to solve question number 5. And so, yeah, I think, sir, we've given quite some hints.
Okay. Yeah. Okay, so fine. That is okay. So we can try to go to the next thing now. Any other questions, or I will move to the next topic? Hello.
Yes, sir. Okay.
Yes, sir. You are audible.
Okay. Okay, so from today, what I was going to do is we will look at algorithms on graphs. Okay, so algorithms on graphs. Now you have seen graphs to some level, and I will maybe ask the TS to cover a little bit more about graphs, various kind of graphs, kind of stuff like that, and the various topics of graph. So you know that graphs are useful for modeling various questions. So let me ask you, have you guys done this thing? Have you used graphs to model various questions, combinatorial questions and all?
Yes.
Yes, sir.
Okay, good.
Sir, we did binary trees in our C course.
You have done binary trees in your C course, that is fine. But say some other kind of, I mean, not even just binary trees, but in your discrete math course, you have done some graphs,
Oh, yes,
right?
yes, lots of.
Yeah, so in discrete math, say you must have done some problems that might not as such look like a graph problem, but can be modeled as a graph problem. Okay.
Yes.
So of course, that's why this beauty of graphs comes in. It's a structure, mathematical structure that is very useful in basically representing binary relations, right? And that kind of gives a lots and lots of powerful things. So many problems where you have nothing related to any graph can be modeled as a graph problem. And then you want to solve that problem in graphs. So of course, so naturally thing is that, okay, do you have some algorithms? Nice algorithms to solve it. So for example, questions that can be asked are, is a graph connected? Or say like, or what is the shortest path? Shortest path from vertex U to V. Or there are things like, can you find an independent set? Are you, so I'm going to throw in some words. If you are not familiar with those words, please shout out, okay? So how to find the largest independent set, or how to find a perfect matching. Or say finding a minimum spanning tree. So there are lots and lots of such kind of questions that are there. So in the next assignment or on the problem sets, so there will be a problem set, by the way, on sorting only, that will be posted this week, maybe tomorrow. Okay.
Sir.
Yeah.
Sir, we know spanning tree, but what is minimum spanning tree?
You know spanning tree, right? So minimum spanning tree is, so if the graph is weighted, if every edge has a weight, okay, then a spanning tree has a weight which is sum of the weight of the edges in the spanning tree. Right? So among all the possible spanning trees in a graph, find the minimum of them, or consider the minimum of them.
Sir, by weights, do you mean that to each edge we assign a real number?
Yes. Yes. Okay. So so that's a good point actually. So what are graphs actually? So graphs by default we write it in this way, right? Where E is nothing but a binary relation. That's it. So this basically, if you just talk about a binary relation, then this becomes a directed graph. Directed graph. Okay. But if I have this extra guarantee that edge E for the as a binary relation, it is reflexive. Not reflexive. It is symmetric, right? Sorry. It is symmetric. I will always assume that this edge E is reflexive. If edge is not reflexive, then this is not considered reflexive. So this is, yeah. So if it is not, then so this has basically says that it has no self loop. Self loop. So if it's symmetric, what does it mean? That if I have an edge from U to V, there's edge from V to U. This is called undirected graph. And now there will be other lots of information that can be stored in a graph. So a typical example is that you have been given a graph, GV, and you're also given a W, where this W is nothing but a map from the edge set to real numbers. Or say positive reals, maybe, or even just reals.
Sir?
Yeah.
Sir, if E is reflexive, that means they all have self loops.
Yeah,
all
I
the
mean,
points
like,
have
so
self
if all of them have self loops, then for we kind of drop the self loop kind of stuff like that.
Okay, but then that also depends on the context, right?
Yeah. I mean,
it could be something like if you're trying to model a finite stochastic process.
Right. So there are self loops are there also. Yeah. I mean, but thing is that if you, yeah, for example, if you are trying to doing some kind of a random walks on them, then you do have self loop that comes up. But usually, if there is self loop at every vertex, then we tend to just drop this. I mean, there's nothing to represent kind of stuff. Everybody is same.
Okay.
I mean, that's not how it changes from context to context kind of stuff like that. Right. Yeah. So there are these various graphs that are there. There are a lot more other things. There can be graphs when each vertex can have weight. They can have some kind of information stored in every vertex. Okay, and so on and so forth. So you have this gives you a huge collection of objects that can be used. So as I told you, so what we will be posting a problem set which has a collection of problems. They don't apparently look like graph problems, but you are supposed to model it as a graph problem. Okay, and then all of these things you will see where the importance of all of these things comes in. So that is a bit of a separate thing from that's like a power of graphs. But now the question is that can we solve this kind of questions? How much time will it take to solve this kind of questions? Right. So let's start with maybe the most basic ones. Is a graph connected? A very important one is this graph connected. Okay. I mean, something that's in the world of COVID, right? With the flights and all, it's like very natural that is there right now a flight that will take you from here, from Kolkata to Santiago, Chile? Is there a flight connection? Maybe not. Maybe these flights have been, half of them are gone now, somewhere it is disconnected, right? Typical example where this kind of problems can come in. There's lots of other. But before I can start with, so let's start with the first question. So is graph connected? Okay, now how is the graph given? So we can think of two versions, the undirected graph or directed graph. Directed and directed. Two cases are there. So what is an algorithm? So you have to do a step-by-step process. So whenever you talk about an algorithm, the first thing that should come in your mind is how is the input given? Is the input given as a, how is the input given? Do you guys have any suggestions? How is the input given?
Sir, matrix.
Adjacency matrix.
Adjacency matrix or incidence matrix?
Adjacency matrix or incidence matrix, right? Okay. So the adjacency
Sir,
matrix.
there is also another representation as lists of neighbors.
Right. Very good. Yeah. So I will just talk about it. Yeah. So the most standard way of useful way of representing it is one of them is this what is called the adjacency matrix. Right. So adjacency matrix is nothing but an n cross n matrix, and you have been given 0 or 1 at every point that represents whether there is an edge between the ith vertex and jth vertex. Right. Now, what is the issue with this problem? What is the input size?
N square.
Input size is n square. So maybe just to make it this, I will say v square.
Right.
So irrespective of how many edges it has, the input is of size v square. So this can be good sometimes, okay, and this sometimes might not be that very good. Okay. The another way of doing it is what is called the adjacency list. So what is the adjacency list that somebody was pointing out? It is in terms of, it's an array that is there of length n. So these are the vertices 1 to n. And from each array, there is a list hanging of arbitrary length, not arbitrary length meaning of different length. Okay. And
bounded by n minus 1.
maximum n minus 1, and they basically contains the set of neighbors of this vertex. So if there's an edge from 1 to say 2, 5, and 3, then I have a 2, 5, and 3. So maybe here 6 and 7, right? So from 2 there is an edge to 1, 4, 9, and 3. So there is not necessary that these edges, these lists are sorted. This might not be sorted also. And but this is the total representation. Note that both directed and undirected graphs can be represented both in this form and this form.
So in a sense, the adjacency matrix is a counting sorted version of the adjacency list, right?
Adjacency matrix is a counting. Yeah, I mean it's like adjacency matrix is basically it is storing a lot more information, right? Yeah, you can say that it's a counting sorted kind of stuff like that, but it's basically storing as a fixed vector.
Right.
It's storing things as a fixed vector, and this one in the adjacency list is not a fixed vector. So in fact, what is the input size in this case? Can you say?
Sir, this is mod V plus mod E.
This is mod V plus mod E, right?
Right.
Why? This is mod
because
V.
we have okay.
Yeah. So go ahead. You explain.
Sir, because we are storing the mod V vertices, and for each we are storing the number of the degree, something equal to the degree of the vertex.
Should be mod V plus 2 times mod E.
Right.
It is actually mod V plus 2 times mod E. That's completely true. It's so this is the number of things here is, I mean, irrespective, even if the graph is completely empty, right? You are expected to store this whole information, right? Which is mod V, right? And here, what is it? What is it? So it is the sum of the degrees of all of the vertices, right? And the sum of the degrees of all those vertices is.
Sir, actually, that in the general case, it should be mod E and not 2 times mod E, because in the undirected graph, we call just an edge. We count an edge as 1, but in the directed sense, it's 2 edges, because it is
In the
one edge.
directed sense, you are right completely. In the directed sense, it is been exactly the number of edges.
So in a sense, if you're looking at a directed graph, then mod V plus mod E is also a
Yeah, you can think of
plausible.
it that way. In the case of undirected graph, it is mod V plus mod E. In the undirected graph, it is mod V plus mod E. But it doesn't matter. Both of them are what is called order of E plus V.
Okay.
Okay. So in the case of adjacency matrix, it is ordered V square. In the adjacency list, the things is ordered V plus E. So this is a very compact way of representing things. Okay. Now whereas this is not a compact way. But if you don't represent things in a compact way, actually what happens is that it becomes easier. For example, if I ask you that, is there an edge between vertex I and vertex j? How much time will it take in this case?
Order 1.
It will take order 1. How many times it will take in this case?
Log n.
No, it can take even
Order n. The question?
If there an edge between vertex I and vertex j.
So why would it take order n? So don't we just need to binary search j in the ith list?
This ith list need not be sorted.
Oh, so this list on top may not be sorted. Okay.
No, list on top or even list on top is sorted. Still, you can think of a list
Okay.
here. This list.
Sir, are we saying is there an edge between 1 and j, I and j, or a path between I and j?
No, just an edge, just a single edge. Just a single edge between I and j. In adjacency matrix, it takes order 1. In adjacency list, it takes order n in the worst case. You see that? Hello?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So there are some other issues. For example, count the number of triangles. How will you count a number of triangles in a graph? Can you tell me? Yeah, maybe this is something that I can just give you as a small problem right away. Okay, count. So maybe I have given you an undirected graph. So let's say to start with, I have said I have given you an undirected graph. G, and I'm asking how many triangles are there in G. Now,
Sir, are you giving any time constants right now? Like
yes.
O(n) square something or anything?
I mean, you have to tell me, give me an algorithm and tell me what is the time complexity. And of course, our goal will be to come up with a better algorithm.
Right.
Okay. So what is the best thing that you can think of? So you understand the triangle, right? It is I, J, K, this kind of.
Yes, sir.
Sir,
Yeah.
Some pieces of the adjacency matrix with determinant 2.
Sorry.
We take the adjacency matrix and we count the number of 3 cross 3 submatrices with determinant 2.
Three cos 3 submatrices of determinant 2. Okay, so fine. How much time will it take? It is not sub. You only take a 3 cross 3 principal submatrices.
Sir, we can multiply the adjacency matrices. And
Okay, and then
sir.
yeah. So
Sir,
okay, forget all of that. Tell me the most simple algorithm.
Sir, I was thinking like we can see this graph as a relation in which the two sets are the vertex set, and there is a relation between two vertices if they're connected. Like
Yes.
if they have a common, if they have edge.
If they were an edge, yeah.
So in this, we are looking for a transitive relation, related elements. For example, if I comma j are connected, j comma k connected, then is I comma k connected.
Correct. Yeah.
So we can always start with a one edge, say I comma j, and then look for the elements with which j is connected.
Okay.
And then check if I is connected with that element or not.
Okay. So you will look at. So basically, if I want to write it here, right? So you will say that for all ij in the edge, okay?
Yes,
and
sir.
then for all k in the neighborhood of I, if k is also in the neighborhood of j, then output yes. Now output 1, right? So I mean you have to count, right? There's the count. Okay. Then I want to count, right? Then count plus count equals to count plus 1, right?
Yes, sir. Some like this is.
Okay, very good. So this is something, this is a pseudocode that you can have, right? Everybody fine with this?
Yes, sir.
Now, what is the time complexity of this? Say, you have to tell me time complexity of this both in the adjacency matrix thing as well as in the this.
Sir, peak of NQ.
It is big O of NQ. Okay, why?
Sir, for that all that one for loop that I comma j belongs to E, it takes big of n square, and then for all k belongs to neighborhood of I, it takes again big of n. So for big of n,
So this is in both of them.
sorry sir, again.
This is in both of them. You're saying, or in both in adjacency matrix as well as in the adjacency list model.
No sir, only for the adjacency matrix.
Okay. Whatever that is. Okay. So adjacency matrix model, you're saying that. So there is this 2 for loop. So this one is a. Okay. So let's see. What is it actually? Actually, it is not. It is worse than this. What
So
you
the if part will also take some
yes,
time, right?
or if part will take some time. How much will if part take?
N.
If part will take order n, right? I can define. This one is take order n in the worst case. Okay. I mean, we are doing a very basic calculation. Now, this one is a loop of order m, right?
Right.
And this is a thing of order n, right? Correct? So
Yes,
it
sir.
will become order m times order n times order n. So this is order m times n squared.
Sir, what is M?
M is the number of, so by the way, this is something I have not told. From now on, almost always, size of the vertices is n and size of the edges is m. Okay, always, unless otherwise mentioned.
So there should be n to the power of 4.
This is the worst case n to the power 4. Right. You can do slightly better possibly here also, because this is not, this is not the n, this is actually d of I. And this is also everything you have to do it. So
D
it's
of
d
J.
of j. So this will basically becomes d of I times d of j. So it will be, if you do it, sorry, this will become summation over I comma j in E d of I times d of j. Now, is that an easy thing to calculate? I don't know. Yeah, I mean, I don't think you can make too much big things. So I think you can do a little bit better. So this is actually less than summation of di times summation of dj, right? So this is n and this is m. So this is order m square, right? So this everything, whatever you have told, is of order m square, which is slightly better than order n square.
Sir, for the adjacency list, also I think it should be same, because if it is unsorted, then I think so it should be same.
But the adjacency list.
Yes.
Yes. That is true. Actually, for the adjacency matrix, now that I think of it, actually, since it is transitive, sorry, so whatever I have done here, I made a mistake here. This is for adjacency list only. So for the adjacency matrix, what happens? Let me use a different color. See, this is order m, this is fine. This is order di, this is also fine. Actually, this is not order di, because now I don't know what are the neighbors of it, right? So I don't know the neighbors of this one. So this will be order n. And this one is how much? If I give you an k and ask you, is this a neighbor of j? This should be
order 1.
1.
Order of n in it was.
No, not order of n.
So why 1?
Because it's the adjacency matrix now I'm talking about. So this green one is the adjacency matrix.
Okay.
Okay. So this will be order m times n, and that's it. So adjacency matrix is ordered m times n.
Sir, why is that O1?
So in the adjacency matrix, if I ask you is K is a neighbor of neighborhood of J, is the neighborhood of J, then what do you have to check? If there exists is J comma K, if there is a in the jkth coordinate,
Okay, sir. Okay.
it is 1 or not, right?
Right.
I just go there, check it and done. Right?
Yes.
Answer, it should be count by 3 at the end.
Count by 3. That is fine. So let's do that one at the end, right? So you're right. You're completely right. So at the end, it should be count equals to count. So basically, it should be because we will be counting it thrice everything, right? Output count by 3. Okay, right. Okay, but now can you in the adjacency list also actually you can do it actually? Yeah, so as adjacency matrix you can do it is here, right? Now you can do better actually speaking, quite a lot better.
Sir?
Yeah.
So can we think of it like this?
There's another issue here. There's another issue here. Issue is that here it is not order m.
That would be n square.
It will be order n square. Because in the case of adjacency matrix, you don't know the set E. Set E itself is stored within that matrix. To find out where there is one, I have to go over all the points in the matrix. So this will be actually order n cube. Okay. Yeah. So you can see that there is two different representations, gives you completely two different complexity measures. One is order n square, one is order n cube. And you can kind of argue that, oh, maybe this order n square is better than order n cube for certain m's. Right? And in the worst case, it's not good. Yeah. Yeah, somebody was asking me something.
No, sir. Sorry. Oh, that got cleared up.
Yeah. There is another thing that you can do in this thing is that, so question is that can you do anything better than this, say, in the adjacency matrix model? So this is something that I can give you another exercise kind of stuff to convince yourself. So say G, let A be the adjacency matrix of G. Then what is A square? What is A square ij? Let's say. Can you tell me?
Sir, if I comma j have one common neighbor, like in adjacency matrix, if there a square ij, some entry is 1 for some ij, then it means that they would have a common neighbor.
Yes. So, okay, so you're right. So this is actually sum over aik akj, right? Sum over k. So it is the number of common neighbors of ij. I'm just doing this multiplication in reals, over reals, not over any non-trivial, not over F2 or doing an AND or all kind of stuff. Right? Everybody with me here?
Yes, sir.
Yes, sir.
What is aij whole cube? I mean, aij a cube of ij. So you can write it again the same way. This is aik, akl, alj, right? Sum over k and l.
It's number of paths of 3 length from I to j.
So this is number of paths of length 3 from I to j.
So therefore, to find the number of triangles, can we always say it like this, that the number sum of the diagonal entries of Aij cube? Because
That is true. Actually, you can do that. So in fact, you can prove. Okay, so this is something I can leave it as an exercise. Okay, show that number of triangles in G is equals to trace of A cube by 3. Okay, you can prove it as an exercise. Now this is, although it seems like why you're asking as an exercise, this is you have already shown it. Yeah, the reason is I have not told you certain things here. Okay, the thing that I have not told you is what is AII. Okay, and here I have assumed that AII is so assume that the diagonal entries of A is 0, then this is true, first of all. Secondly, can I say the same thing for A to the power 4? So what is trace of A to the power 4? That is not number of 4. That is not number of 4 length.
So because in that we can also count paths like 1, 2, 3, 2, 1.
Right, exactly. You can have paths of this form. From here, go there, then back, then go there and back. That is a valid path that would contribute to something like A to the power 4 II. Okay. But in the case of triangles, it doesn't. But you can still show. Okay, so this is another thing. So think about it. What does the trace of A to the power 4 present? So now, why is so now? Okay, so this is one way of computing the triangle. But why is it good? Now, this is something that is very useful, and this is something that I don't know whether I will have time to prove it to you, but let me just tell you still. And as a statistician, you will need this kind of stuff. Okay. So if I give you, or what is the time complexity of multiplying two matrices, the n cross n matrices? What do you think? I give you two matrices and I ask you to multiply them.
So the usual method
do we
would be
consider the addition of all the entries as a single step or multiple steps?
So let's say that I say that the only I want to minimize only the the cost of multiplication is order 1, and the cost of even addition is also order 1. It doesn't matter here. Say, actually, you can make this one order 0 also, and then also it's the same. If you want to say it's free, then let's just for consistent, let's say cost of my addition is also order 1. Multiplication meaning I mean multiplication of two integers or two numbers. Addition means also addition of two numbers, not addition of two matrices.
It should be O(n) cube, right?
This should be O(n) cube, right? Because you have these two matrices. I have to take one thing from here. I have to take one thing from here, right? I have to look at, so basically for all rows and all columns, so R and C, right? So for all R from 1 to N, and for all C from 1 to N, compute. What do I have to compute? I have to compute summation of, so this is, let's call this one A and this is B. A R I, sorry, made a mistake. Yeah, A R I B I C, right? Summation over I. Now this will give me the RC coordinate, and that's what will be done. So this, how much time does this take? So this has n additions and n multiplications, so it's order n. So this thing is order n, this is order n, and this is order n. So the total cost is, so there's a for loop, which is n square for loop, and each of them is order n. So the time complexity is order n cube. Everybody fine with this?
Yes, sir.
Yes, sir.
So now here is the thing that I think I'll go back to it much later on in your course, maybe at least not, yeah, not in the next few weeks for certain. But this is not the best algorithm. Okay, so if you are interested, you can take a look at this one. So there was a guy called Strassen. He came up with a beautiful technique. Okay, basically what he did was that he says, okay, I have these two matrices, right? If I split up into four things, okay, so this is A1, A2, A3, A4, B1, B2, B3, B4. What is the standard way of producing the product?
Just like the usual way, like A1 time, the first block will be A1 B1 plus A2 B3.
A1 B1 plus
A2 B3.
A2 B3, right?
Yes, sir.
Similarly, it will be A1 B2 plus A2 B4, right? A3 B1 times plus A4 B3, and
A3B2.
A3 B2 plus A4 B4. So this product basically becomes, see, each of them is of size n, right? So if I say that T of n is the time taken to multiply two matrices of size n, then this can be broken up in this beautiful way. And then, okay, I will do how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplications of size half each. So he can say that this T of n can be written as 8 times T n by 2. Okay. Okay.
Sir, and there is the addition bit as well, right?
And then there's addition bit also. It's a constant or something, order n squared. Okay, that's not.
This is still n cube, right?
This is still n cube, unfortunately enough. This is still n cube. But he looked at it in this particular setting. And can I do it in some other way? Okay. And I will leave it to you. Go back, think about it, look at the internet, do whatever. Okay. He proves that all this, instead of doing these 8 multiplications, you can actually save one of the multiplications. by doing some very clever manipulation, he proves that you can replace this 8 multiplications to 7 multiplications.
So then it becomes order of n to the power log
Something.
2 based 7.
Yes.
Okay.
And then this will end up becoming, sorry, just one second. Hello? না ISI কি হয়? ISI এর উপরে হেডিং দেওয়া যেটা। হ্যাঁ হ্যাঁ আমি এসি অনুযায়ী তাহলে একটা ঠিক আছে আমাদের ISI নামটা থাকবে ISI ঠিক আছে hello sorry yeah so this will end up becoming n to the power 2.78 or something like that. Okay, so this is what is called a Strasson's algorithm, one of the most useful algorithms ever designed, because as you know, multiplication of matrices are very useful things, right? And here, using some beautiful trick, he proved that you can reduce the time complexity from n cube to n to the power 2.78. In fact,
how much helpful is this?
How much? What?
Helpful is this? I mean, this is, I mean, the amount by which it is reduced is small, right?
Oh no, that's a massive one. That's a massive one.
This is small o of n cubed, right?
This is small o of n cube. The reduction is massive. So think of that. You guys work with data, right? You do all these kind of various statistical processes and all those things, statistical measures and all. You have to take things like you have to take determinant, you have to take this multiplication of this very matrix with that matrix and so on. All of them, they how big are they? So n is something of the order of the number of data points that you have. That can be in the tens of thousands possibly, right? And you are saving n to the power 0.22, meaning put n equals to say 10,000 and see what happens here, right? N to the power, this one is basically 100 or something like that, 50 or 100 or something. Even at the level of 10,000, this is a 50 times improvement. Now, if n is massive, something like what happens in the case of, say, a census data kind of stuff like that and all, then the improvement is terrific improvement.
So can we improve this further? I mean, can we reduce this 7 to 6?
Yeah. So after this algorithm, there have been lots and lots of work. And right now, the algorithm that is there, the best known algorithm. So I might come back to Strasson's algorithm and explain you the Strasson's algorithm, but whatever I'm going to tell now, I will not be doing it in this course. Okay. So best known algorithm is n to the power not point, what cannot be. So first of all, you realize that it has to be, by the way, another thing is observation, it has to be bigger than n square, right? Because at the end of the day, I have to produce n square different points in any case, right? So you don't expect to do anything better than n square. Any algorithm has to have n square time complexity. So the best known algorithm is n to the power 2.37. And this algorithm has lots and lots of nice ways of doing it. So there is some combinatorial way of finding the algorithm. There is a group theoretic way of solving it. So there's some very nice result that has been done maybe 10 years ago or 7 years ago, where they showed that obtaining better algorithms or obtaining, matrix multiplication algorithms is same as obtaining certain kind of groups, designing some kind of groups, and using that they can also achieve this result. And what is belief? Okay, so now this is not something we don't have. The belief is that this should go down to order n square. Okay, so you can understand that how much improvement that can be. Okay, so thing is that you can really progress a lot.
Sir.
Yeah.
Sir, in this scenario, you have said that in the example, n is equal to 10,000. You said that n to the power 2.78 produces a massive effect in our computation.
Right.
Now, in the case, suppose I have two algorithms, A and B, and A takes n square steps and B takes 2 n square steps. But both of them, we denote them as big of n square.
Correct.
But in that case, if I use in the same example with A is equal to 10,000, there will be a massive change, massive improvement in the algorithm.
You're right. The reason is that here why we are interested in is that as n increases, right?
Yes, sir. Yes,
as n increases, your gain becoming more and more impressive, right? Whereas in the order case, you increase n doesn't matter. It is still a constant improvement only. Okay, so that is one thing. The other thing is that you are right that in terms of the representation kind of stuff like that, in implementation kind of stuff, even compared to n squared, an algorithm of n squared by 2 is also improvement. There is no doubt about that. And if you talk to the programmers and all, if you can keep a 10-fold improvement in the constant, theoretically both of them are order n square only, but in terms of practice and implementation, it is massive. So I think this is where this theory and practice take slightly two different turns. Okay, for people who are actually implementing it, every constant matters. From the theoretical point of view, also there are people who work on these constants also, but we have to kind of still quantify certain things, right? And for that, we kind of say that, okay, this improvement going from n cube to n to the 2.78 is way better than going down from n cube to n cube by 10 kind of stuff like that. Okay, so one is this asymptotic. So you are completely right that if you are really talking about implementation algorithms, every constant matters. But if we are just getting focused on all possible constants, we will not be able to make much progress in, at least in this course for that matter. Okay, so that's why we focus on asymptotics, and you will realize that this one asymptotically is way smaller. It's smaller of n cube, right?
Yes, yes.
Also, in considering all the algorithms, we are not really bothered about if we can do it using parallel computing or something.
Okay,
like
that's
that.
another goal that comes up. So those are the things that comes up. Okay, I mean there are issues about it. Which algorithms can be parallelizable? Which algorithms cannot be parallelizable? Which
So,
algorithms?
I mean, in this one, if we are do it in 4 computers, and I mean,
you can do that. You can do parallel things. That's completely right. So there are lots of this kind of advantages also that are there. So when people talk about algorithms as a actual view who actually end up writing code for softwares and algorithms and all those things, they have to keep in mind all of these things. Okay, I mean you are running this algorithm in a particular kind of program, like programming language, that what kind of operations that programming language have and so on and so forth. Okay, I mean certain things that I don't know whether you guys have observed it or not. Like, so all of these things matter. Like I'm taking a small detour here, and I'm thinking, like for example, if I just ask you to solve A into B plus C, there are some programs they do it as you first add B, then add C, and once you have that, you multiply with A, and then B, and then C, and then this B plus C. The total number of operations is 1 and 2. And there's some computer, some programming things, they open it up by saying, oh, this is equals to A times B plus A times C. And the total number of operations therefore becomes, okay, 3. 1, 2, 3. So this operation is 2 operations. This is 3 operations. Now, why this is useful? This is useful because you can do it in small and small stuffs. Okay, there's a lot of parallel things can be done and all those kind of stuff. Maybe this cannot be done. So the number of operations are different. So you can see that there can be a 1.5 times improvement in this kind of things. So people who are actually interested in programming, they have to know a lot of things. A good programmer will know the need for the problem, how much resources do they have, which program should I, which programming language should I pick up for that purpose, what kind of course, there's the data structures and algorithms and all. There's a lot of things that goes on there. Okay, but in this course, we are not worried about this kind of use of improvement. They are all very important improvements, and for people who are writing programs, that is also very important. We are more interested in the much more theoretical improvement at the level of algorithmic understanding. Okay, and that's why we are more interested in the asymptotic improvement rather than the constant improvements. So yeah, you are completely right. So that Statson's algorithm has parallelizable features. That also is very useful. And there are a lot of other features that are there. Simplicity is another feature that is used a lot. Like for example, this algorithm is not known to be simple. This algorithm is theoretically very nice, but it's not known to be simple. Whereas the Statson's algorithm is reasonably simple. So still people, many of the softwares use this one rather than this. Although this, you can see that is a significant improvement of this. But theoretically, this is what we have right now, and we believe that this can go down to order n squared. And there are lots and lots of results that happened. It's the cutting edge of research in many ways.
Sir, can we prove something like there must exist at least one algorithm, at least one O(n) square algorithm, which can perform a matrix multiplication?
We don't have that. I mean, that is, I mean, yeah. So
Sir, I mean, do you even know about the existence?
No. We don't even know about existence. Okay. But I mean, we know certain other relationships, like what does finding this mean? So this, if you can find something like this, it would mean certain combinatorial results in what is known as sunflower lemma and all. So there are lots of such kind of results that can be produced from there. Okay. Fine.
Yes, sir.
Okay, so coming back to this graph thing, so that means for finding triangles, if you do multiplication, okay, so if you're trying to do it by trace of a cube by 3, so this will be how much time? It becomes order n to the power 2.37. Oh, by the way, because this number keeps on varying with time, because people kind of keeps on improving it, so we usually denote it as n to the power omega. N to the power omega is considered to be the cost of multiplying two n cross n matrices. That omega currently is sitting at 2.237. That might very well be that next year it will go down further. Okay.
Sir, for the triangle case, won't it be n to the power 2 omega?
Why will it be 2 omega?
Because we are multiplying 3 times. First
Any model. So
a
you
square and then a square that we take.
and then this is b, then b times a. How much is
Yes,
it?
sir.
This is ordered n to the power 2.37 or n to the omega, right?
In omega, and that is also in omega.
So this is how much?
Oh, sorry.
The addition.
Yes, sir. Yes.
So the total time complexity is order n omega. Okay. So anyway, so we have come to, so whatever. So we have seen this the simple problem of finding triangles in graph in the adjacency matrix model, in the adjacency list model, and so on and so forth. And there are various different techniques and things that keeps on going here and there. Okay. So we have kind of convinced that in the adjacency matrix model, you can get it down to n to the power omega. In the case of adjacency list, it was n squared. Okay. And
Sir, in the adjacency matrix, can't we bring it down to n squared, as in an undirected graph, all we need to find is if we focus on the lower triangle, let's say, because it's a symmetric matrix. So all we need to find is triangles of the kind where you have entry 1 at some I comma j, then some j comma k.
yes,
and then
but that triangle is of the form. How many triangles are there? N choose 3, right?
Sir, there are not n choose 3, right? Because we are looking at a very special triangles, which are just of the form of.
Are they? Think of it. I mean, in the case of graphs, right? I'm checking whether there is an edge between I, j, and k, right?
Right.
So it is like from the end you choose any 3 of them, and it is there a triangle.
So actually, if we let's say we take any 2 elements from a single column.
Yeah.
And then we need to just check for the third element is already determined.
Right.
So, oh, okay. I'm sorry. Right.
Right.
It got clear. Right. Yes.
Okay. So basically, yeah. So I think I will stop here today. We have got hold of some understanding of these 2 inputs that are there, the adjacency list input and the adjacency matrix input. And in the next week, I will be going into these 2 things. Basically, what the basic algorithm is that given a graph, and I will, we'll mostly think about it in the adjacency list kind of stuff. Given a graph, check if G is connected. Or basically, what I want to do is that I want to keep on visiting edges and see all the edges that I can visit. Okay, so basically this is called a graph traversal. So I will basically, if I have a graph, I want to start from a vertex and traverse the whole graph. I want to walk on the whole graph. Okay, and I want to do it as quickly as possible. Of course, I don't want to revisit the vertices again and again and again. That's too costly, right? So I want to traverse it. Now this might sound very trivial kind of stuff, but say when you search something on Google, right? What Google does is Google does what is called the web crawling, right? What they have nice name for it. So any search engine crawls the web and finds out whether that website or that link contains your phrase that you're searching in the Google search engine, right? And that is nothing but looking at the web graph. Web graph is the graph where each node is a link or a web page, and there's a connection between one to the other if there is a link from one to the other. And in this whole web graph, can you walk and find it out? Okay, can you traverse the whole graph and find out all the vertices? That has your necessary property. So the graph traversal is a very useful thing in many contexts. Okay. So if you want to think of it physically, think of it that there is a city, right? Or they say inside the ISI campus, there are these various buildings that are there, and there are paths connecting various buildings, and your friend is hiding somewhere, and you have to go and find out where is he hiding or where are they hiding. So you have to kind of go and look at all the various buildings, right? You have to traverse the whole network. Of course, if there's no road from this building to the next building, this building and another building, then you cannot go from here, right? So you have to walk along the graph. So graph traversal is a very big topic, and we will be doing two of the most well-known graph traversal techniques or things that are used. They are called the depth first search, DFS, or depth. Have you guys done these things in your graph theory?
No, sir.
No, sir. That's just mentioned depth first search and BFS.
Yeah, so these are the two techniques of traversal of graphs, but these are not the only ones, by the way. But we will be just sticking to these two, and they have very nice properties, different properties and different things, and that comes up. That's very useful at various times. Okay, so I think what I will do is I'll stop now. Tomorrow there is a tutorial. I would like the TS to then take the tutorial, and I would ask them to maybe do a little bit of stuff on use of graphs in modeling. So how can one graph be, how can graphs be used for modeling various problems and so on and so forth. And yeah, this kind of stuff. So in the next week, I think the next week is there, right? There's no holiday next week, right? Hope so. I think next week there is no holiday. Yes, next week I have both the classes. Next week I will be doing this TFS and BFS. Actually, there is 3 consecutive weeks times in the class that I have before there's a 1 week, 1 class break for Diwali. Okay, so that's it for now today. Any questions? If you have any questions, let me know.
Sir, if we want to determine the connectedness of a graph using the adjacency matrix, can we do something like compute a plus a squared plus a cubed all the way up to 8 to the power n minus 1?
You can.
And then check whether it has any zeros.
Right. Of course you can do that. Right.
Right. Then that will be an n to the power omega complexity algorithm.
That will be n to the power omega. Actually, okay, you have to multiply all of them, right?
Right.
And that would, yeah, you have to do it a bit.
We don't have to multiply all of them. We have to just add all of them.
Yeah, but how do you get n to the power omega? N to the power n. So a to the power n.
Sir, we don't actually have to do that. In certain cases, we can just find I minus a inverse.
Sorry?
In certain cases, we can just find I minus a inverse, right?
Okay, so that is true. I mean, yeah, I minus a inverse. Yeah, you are right.
If it is invertible, then we can just do that.
Yeah, actually, inverse is also same cost as finding inverse is same cost as
multiplication.
Okay. Okay. So yeah, so you will get an n to the power omega bound, but n to the power omega bound is a bit costly. So you can actually do better traversals in linear time.
Okay. Oh wow. Okay.
That's what we will be doing. So both this DFS and BFS will do this traversal in linear time, meaning in order n plus m. Okay.
Yes.
Any questions?
Sir, we are supposed to turn in the assignment.
Yes.
Within Wednesday midnight, right?
Wednesday midnight.
I mean 11:59 p.m.
Yeah.
Okay, sir. Thank you.
Sir, I think in the classroom it's still saying the date is still saying.
I'll change that. Okay. Don't worry. That doesn't mean that you cannot submit. You can still submit. Okay. The submission of that is pretty much something you can do. Okay.
Thank you, sir.
Oh, thank you.
Thank you, sir.